Number 20 here we have an optimization problem. First thing I like to ask myself is what is it that's being optimized here? And frankly, minimizing the cost. We are trying to optimize cost, so our primary equation is going to be a cost function. I don't know exactly what that is yet, but at least I've got a target in sight. It appears as though since they're giving us this information, we're going to need some kind of secondary equation. I'm just going to go ahead and write down the fact that the volume of this thing, which is a cylinder, so volume of a cylinder, you think about it like a circular base with a height perpendicular to that circle. So to get your 3 dimensions, you take the area of the circular base, which is pi r squared, times the height of the whole thing to get that 3rd dimension, which makes it a volume. But that volume is supposed to equal 24. So pi r squared h equals 24 is our secondary equation. So it's open at the top, the cylinder is. I have to draw things. That's not my forte, as you can see. But this is open. So if I'm looking for surface area, I'm only going to include this bottom circle as well as the area of the sides. Alright, so cost of the material used for the bottom is 15 cents a square inch. Well, the bottom's a circle, and circle has an area of pi r squared. So whatever your area of the circle is, pi r squared, that's going to have to get multiplied by 0.15. Add on to that the surface area of the sides. Alright, if you don't remember what surface area of a cylinder is, I don't either. I just try to kind of figure it out as I go sometimes, I guess. You can look it up. But frankly, if you took a cylinder and cut the sides off, made like a cut like this, it would spread into a rectangle. I know the area of a rectangle is base times height. So I can take the base of this curved up rectangle is also the circumference of the top. The distance around the top is also the distance around this bent up rectangle. And that's pi times diameter. But then you also have to multiply by the height to get the area. So the rectangle's area is the circumference of the circle times the height. And that's going to get multiplied by 0.05. This crazy equation here is what we are trying to minimize. Let me clean this up a little. 0.15 pi r squared plus 0.05 pi dh. And maybe I shouldn't call it diameter because I've got radius here. So I'm going to call this 0.15 pi r squared plus 0.05 pi. Diameter is 2 radii height. So I'm just subbing out the diameter with 2 height, or 2 radii. So 0.15 r squared plus 0.05 times 2 gives me 0.1 pi r h. Now I've still got 2 pesky variables here. I've got r and I've got h. And that's what this secondary equation is going to help me out with. I'm going to isolate the h in this equation. I get 24 over pi r squared. And that allows me to take this h out and sub in 24 over pi r squared. And it's really going to be some algebra here to clean this up. I've got an r on top against 2 r's on the bottom. Well, heck, I've got a pi on top against a pi on the bottom. So this pi kills that pi, and this r kills one of those r's. And that's how I end up with this cost equation. And now I've just got radius instead of multiple variables. So I'm trying to minimize cost. I need the derivative of cost. Bringing the 2 down gives me 0.3 pi r plus, oh great, multiplying all this fun stuff together, I get 2.4 pi. And now I've got to differentiate r to the negative first. So that would make me bring down the -1 and drop this to an r to the -2. I've got a -1 times a 2.4. That gives me -2.4 pi over r squared, I guess you'd say. I'll do it this way. Put the 2.4 pi on top, the r squared on the bottom. I've got the cost derivative, because cost is what I'm trying to optimize. I'm going to force it to equal 0. When you've got two terms that equal 0, it's convenient often to just slide one term over to the other side and set the two things equal. If I cross multiply, I get 0.3 pi r cubed equals 2.4 pi. I can divide away the pi. I can divide away the 0.3. Well, this divided by 3 would be 0.8, so it's going to become 8.0 when I divide by 0.3, which means r is 2. Now, that might give me a max, that might give me a min. We've got to verify that we're actually getting a minimum cost and not a max. Let's see, how can we do that? We could figure out the second derivative and plug this into the second derivative and hope for a negative or a positive second derivative, which would give us a concave up cost graph and make this a min result, a result that yields a min. Another way would be to plug like 1 into the first derivative and 3 into the first derivative and see if we are changing from a negative result to a positive result. I really don't care which way you do it. You should do one of the two. I'm going to leave it up to you. But you should find that this yields a min. It does ask for the dimensions that will minimize cost. So I need to find the height. Well, if height is 24 over pi r squared, that's 24 over pi times 2 squared, or 24 over 4 pi would be 6 over pi. So the dimensions would be radius of 2 inches, height of 6 over pi inches.